So I'll begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for this class and for your creation that we can study it. Help us to understand what we can today about differential equations, and just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I get the, here's the attendance sheet. Thank you. So today, I'll begin by talking about the so-called Dirac Delta function. Okay? I'll put function in quotes because it does beg certain questions. So the definition of the Dirac Delta function is this. Delta, let's say of t minus a, is defined by the following fact. The integral from 0 to infinity of f of t times delta of t minus a dt is equal to f of a. All right. So where, f of t is some function whose domain includes t greater than or equal to 0. So just to give you a quick slogan here, I always tell students the way to understand the Dirac Delta function is that it turns an integration into evaluation. It's exceedingly strange, this thing. Let's look at an example of it. So, just a few, just warm-up examples here. What if we had the integral, say from 0 to infinity of just, Dirac Delta function? Well, I guess my definition is too narrow. Let's just say for t, whose domain let's say is r, and let's just make this integral go from minus infinity to infinity. That's a little bit more accurate as to the real definition. All right, so if I have the integral from minus infinity to infinity of delta of t minus a dt, what's that equal to? Now here, just to be clear, a is, some given real number. That's the context here. And again, here, a is just some real number. So you guys tell me, what's this equal to? Just 1, right? Because the function here is just the constant function 1. So the answer is just 1, which is really kind of weird, right? So, on the other hand, if we had the integral, say from, say 1 to infinity of delta of t dt, what would that be equal to? Or the integral, we could even go from 0.00001, whatever, as many zeros as you like. What's this equal to? What are these equal to? 0, right, because I guess that's not clear yet from my definition. Another, to complete the definition, I suppose I probably should say this. I mean, I don't know, maybe it's a corollary, however you want to look at it. But this is oftentimes, you'll see people say this. Delta t minus a, it's infinity. if t is equal to a, and it's 0 if t is not equal to a. That does describe its behavior pretty well. All right. So what would this say then, like geometrically? This says what? The area under y equals to, delta of x minus a is what? It's 1, right? What's a graph of this? It's 0, right? Right up until a. And then you've just got this infinite spike, So do you know anything in nature that's behaves like this? Like what anything physically kind of has this kind of characteristic? So two things come to mind for me immediately, something that has this kind of mathematics to it. The one is like a point charge, right? If you think about a point charge, there's no charge anywhere except for the point where it is, and then there's a finite amount of charge, right? So a point charge is like this, right? If I was to write a formula, so suppose I've got a charge q here, right, at position, suppose this is the x-axis, and so this is at x equals to a. Then I could say lambda, which is the charge per unit length, the charge density, the linear charge density. A good formula for it, if I've just got a point charge q at x equals to a, would be like q times the Dirac Delta function of x minus a. See, if I integrate over some, interval, let's say x1 to x2, the charge density, right? That's supposed to give me what? That should give me the charge on that interval. Should give me the charge that's on that interval. And you see how that formula works, right? Unless, if you're integrating from x1 to x2, the only way that this is either what? This is either equal to q if a is an element of this interval, right? Or it's 0 if otherwise. So the Dirac Delta function allows us to describe the localization of charge, for one thing. I left a hammer. I have a hammer in my office at the moment because I'm trying to fix a bookcase that I'm about to inherit from the conference room. Woohoo! But if you could imagine hitting a nail with a hammer like that, that's the kind of profile you have of the force, right? So like hammer hitting a nail, If I was to graph time versus force, if the hammer hits the nail at like time t naught, right, then basically zero force, and then there's just a spike, right? There's a spike of force. Now, I would say that, of course, there is some kind of characteristic, delta t over which the spike of force is applied to the hammer, right? The hammer strikes a nail. It's not absolutely instantaneous, is it? But suppose you don't know the details of the delta t, If that was the case, if you wanted to ignore the particulars of the actual amount of time it takes for the hammer to impact the nail and drive it into the wood, then the Dirac Delta function is a pretty good device to capture that idea. What's the area under the spike? What's the meaning of the area under the spike? Physically speaking, do you guys remember? What's the area here? How about this? Do you guys remember the net force is equal to what? The change in momentum per change in time, right? F is dp dt. So if I look at the integral from say time 1 to time 2 of the force, that's equal to the integral from t1 to t2 of dp dt, right? Which is p of t2 minus p of t1. Do you guys remember what the name of this is? That is impulse, right. So this is the impulse. So physically speaking, if you want to, model a hammer hitting a nail with a Dirac Delta function, then you need to know the impulse that the hammer delivers to the nail. And let's see here. So we could do this. F is equal to something like J naught Dirac Delta function of t minus t naught. This would be the formula for a hammer hitting a nail with impulse J naught. Right? If you integrate that over time, you either get J naught if time naught is in the interval time, or you get 0. Right? Anything else we can say about the Dirac Delta function before we get back to Laplace transforms, which is, of course, what we're after today? What would the derivative of the of the Dirac Delta function be? Oh, I don't even know about that. That's too hard to ask. How about this? What if I looked at the unit step function? So u of t minus a we defined last time, right? It was 1 if t is greater than a. It's 0 if t is less than a, right? And so that looks like it's just 0, right? And then it jumps to 1 immediately, right? And I'm leaving the definition at a up to you guys. Now, is that how physical switches actually work? Is that, like, do physical switches actually work that? Like, if I go back here and, it's good to give this lecture in this room. It's like one of the only rooms I can do this. But if I do this, right? Was that an infinitesimal time between when I hit the switch and when the light turned off? I mean, the answer is no. Can you quantify it? I can't, right? It was probably a couple milliseconds or something, right? I mean, it's really, really fast. But nevertheless, this isn't actually a true physical picture of what's going on. The true physical picture is probably something more like, this is at A. It's 0, and then there's some finite time, it ramps up to 1, and then it goes on, right? And again, there's some characteristic time for the switching to happen, And so if you think about that, what's the derivative of this thing I just drew? I'm going to draw the derivative in blue on the same graph, if that's okay with you guys. What's the derivative of this right here? It's 0, right? No change, no change, no change, no change. Sudden large change, and then back to 0 again, right? I can do better. So something like that. I mean, there's just a sudden spike, basically, and then it drops back to constant again, just like that, right? So what about this one? If you were to be so bold as to try to draw the derivative, it would be like 0, and then there's a spike, and then back to 0 again, right? And so for this reason, we can meaningfully say that the derivative of the unit step function at A is what? Right, it is the Dirac Delta function. Now, if you find this totally reasonable, then you obviously don't remember your calculus 1, right? What did we learn in Calculus 1? If a function's differentiable, what is it? Among other things. Differentiability of a function implies continuity of the function. Is the unit step function continuous? It is not, right? It is not at A. And yet I'm saying that we're differentiating this discontinuous function to get this quote-unquote Dirac Delta function. As you can see, we have left the bounds of ordinary calculus, right? This is not part of the theory of functions. This is part of a larger discussion. If you want to know the careful mathematics of it, you have to look up what's called the theory of distributions. So distributions are generalized functions. Basically, their whole, like, the Dirac Delta function is something like the limit of a bunch of functions that are like tent functions that all have the property that the area under the tent is 1. And in some sense, the limit of that sequence of functions can be understood to be the Dirac Delta function, quote unquote. But anyway, there's a theory of distributions. You can look it up. I mean, it probably doesn't matter to you guys, but just saying. Okay, so what's the Laplace transform of the Dirac Delta function then? So let's see here. If we calculate the Laplace transform of delta of t minus a of s, we've got integral from 0 to infinity of f of t times delta of t minus a. I forgot my very important e to the what? Minus st. And why is this f here? What's wrong with me? Goodness gracious. I need to drink more coffee. Give me a second. So you guys better be done with that integral by the time I get back to it. Answer? E to the what? S times what? This makes integration turn into evaluation, right? So we just put t equal to a. Done. So there you go, the Laplace transform. And if we had f of t times...
Not 1 over s e to the sa?
No.
Sorry.
You're fine, you're fine. So if I had f of t times delta of t minus a, then I would have the integral from 0 to infinity of e to the minus st, f of t, delta of t minus a. What do you get then? This time the function is this, right? So you evaluate that function. I'll write out a step this time. E to the minus st, f of t, and we're supposed to take that and evaluate at t equals to a. All right? Which gives me e to the minus sa times f of a, apparently. All right, so let's, now that we know how to take the Dirac Delta function, the Laplace transform of it, let's solve an example, physical example. So example, what am I on? 2-ish? Yeah. Suppose you have a spring with mass m equals to, let's say 1, and spring constant k equals to, and we'll make it 4 for fun, and I guess I could put units in here. Let's put, say, 1 kilogram, and what are the kx? Newtons per meter, I guess, is the units for the spring constant, right? Newtons per meter. And an impulse is of let's say 10 kilogram meters per second is, delivered to the spring mass system. I should probably say the mass. You usually hit the mass, not the spring, don't you? Deliver to the mass at t equals to, let's say, 3 seconds. Right? If the initial position x of 0 is equal to, let's say, 2 meters, and the spring, x prime of 0 is equal to 0, then find the equation of motion. In other words, find x of t. If you guys don't mind, I'm going to omit units from here on out as to reduce the clutter. But of course, physically speaking, it is we should have consistent systems of units to write down the equations we're writing. It's okay. I won't remember it when I grade your final or anything. Let's see here. So, sorry, it's too much fun. Plus 4x. So x prime prime plus 4x. This is, well, let me back up a second here. So we have m times the acceleration is equal to minus kx plus the force of the hammer, right? Hammer time. And so that gives me the following equation. It gives me x, we'll use some dots in here for a change, double dot, minus k was 4x is equal to, what's the hammer? 10 times the Dirac Delta function of t minus 3. All right?
X prime prime plus 4x if the kx is negative.
Yeah. Thank you. It beat me to it. Very good. So we got that, right? Now, next move, take the Laplace transform of this thing, right? So the Laplace transform of x double dot plus 4x of s is equal to s squared times big X minus s times the initial position, which is 2, minus the initial velocity, which is 0, plus 4 times big X. And that's going to be equal to the Laplace transform of 10 times the Dirac Delta function of t minus 3 of s, which is just e to the minus 3s. What'd I do? No? Okay. The dot is just a time derivative, right? So solve this for big X. One more step here. S squared plus 4 times big X is equal to 2s plus e to the minus 3s, right? Now solve for big X. We've got big X is equal to 2s over s squared plus 4 plus 1 over s squared plus 4 e to the minus 3s. You have to treat the term with the exponential in s and the term without the exponential in s. You have to treat these separately. All right, they require a different approach. Now we take the inverse transform. So the solution we're looking for, x of t, is in fact the inverse transform of this big X, right? And so we've got the inverse transform of 2s over s squared plus 4, right? Plus the inverse transform of, let us say, 1/2 of 2 over s squared plus 4 times the exponential. Now, why did I put the half there, guys? Why do that? Right, I need the 2 for the sine's Laplace transform, right? So to inverse Laplace transform, I need a 2 there. So the first one, this first piece gives me twice cosine of, well, 2t. And then on the other piece, I get what? 1/2 the sine of 2 times parentheses something times the unit step function of t minus 3. But notice that the unit step function gets paired with an evaluation at t minus 3 of the Laplace transform. So there you go. That's the formula right there. That's the solution. So I'm using the Laplace transform rules that we learned last time for the unit step function, right? Does this, let's think about this physically. Does this make sense physically? Like, what's going on here? You got the spring. It starts out at rest, but it's stretched out to 2, you know? And then it starts wiggling. And I'm not sure, let's see here, what happens at time 3, you're at what? How many cycles do you go through? If I was going to do this graph well. From time 3, what's the period of 2t? 2t, 2 times the period is equal to 2 pi, right? So my period is pi. So at time 3, we're almost full cycle from the start, right? So I'm like almost full cycle here at 3, because the period's pi. And then what happens is the hammer hits the spring, hits the mass, whack. And then after that, we have, you know, that still, but now plus 1/2 this. What is this? So initially, this is just 0, right? But as time goes on, you know, as time goes on, I'm not sure exactly what happens right here. I have to analyze it more carefully, but I'm going to put a question mark here. I don't want to get into those details right now, but eventually it's going to be a larger oscillation, right? How big? Well, the amplitude, so this right here, I'm pretty sure that the amplitude of the resulting phase, you can do the square root of 2 squared plus 1/2 squared to get that. Which is, you know, whatever that is. For square root of like, well, wait a minute. I can't do math. What's 4 plus 1/4? 9 over 4. Oh, 17? Oh.
Yeah,
I was thinking 9 over 4, so I wanted to believe you. So square root of 17 over 2 is the new amplitude. You know, like, see, because what's happened here is that the hammer has imparted energy, right? And I think the way I've set this up, it would somehow be hitting, at that moment, it's hitting the spring in the same direction it's stretching out. So it's like, it's somehow hitting the spring in such a way that it's making it, I'm not compressing the spring, you know? It's actually, the hammer's hitting the mass in the direction of its motion, so it's increasing the amplitude. I'm pretty sure if I made this, if I made the impulse negative at that particular time, then I would be striking the mass opposite its motion, and then the resulting amplitude, I believe, would be smaller afterwards. But this is just, I'm pretty sure about this. I'm about 90% sure on this because I haven't done this stuff too much, but there's another problem where we have like the sum of sines and cosines, and basically you can think about them. I mean, I'm conjecturing that this is the amplitude, but there's some trigonometry to do here. You know, I could be off. Let me put some quotes. Put some scare quotes on all this. These are conjectures, all right? But the formula that I boxed is not wrong. That much I'm pretty sure about. Any questions? No? All right, well, let's look at some more. Let me get this. Oof. So I hope you see, you know, if you're given a choice, solve a differential equation with a, man, my computer must have turned off or something. Everything's gone. If you're given a choice between solving, yowzers, a differential equation that's got a unit step function as the force, or if you've got a choice to solve a differential equation with the Dirac Delta function as a force, you choose the Dirac Delta function. The mathematics is way easier. You notice that we didn't end up with like a cubic in the denominator for that problem, right? When we take the Laplace transform of the unit step function, we get that reciprocal in S with it, which makes things much less pleasant. All right, so this is the things I just went over with you guys. I tried to draw these things for you today. Here's yet another example. We'll go through this one. If I can find my, oh man, oh, here they are. So here we have mass 1, spring constant 1, initially at rest and initially unstretched, right? So that's kind of the most boring possible thing. It's just sitting there doing nothing, minding some business, and then the hammer hits it at time 0. So here, and here I'm just using a so-called unit impulse. Impulse is 1. So sometimes the Dirac Delta function is also called the unit impulse function because it has an impulse of 1. So we apply Newton's second law. We have to solve x prime prime plus x equal to delta of t. And then we do what we usually do, which is to take the, thanks. Oh, you already got it, cool. Laplace transform, right? But the Laplace transform is super easy here because the initial conditions are both 0. So we just get s squared big X plus x equals to that, right? But in this case, the Laplace transform of delta of t is e to the 0, which is 1. So we get big X is equal to 1 over s squared plus 1. Take the inverse transform. There you go. This problem is very simple. And it makes a lot of sense, right? So the spring's just sitting there doing nothing. Then you hit it with a hammer, whack, and then it starts oscillating after time 0. We could easily well change this problem. Instead of putting like delta of t, put like delta of t minus t naught, right? If you replace delta with delta of t minus t naught, everything goes through the same, except you get a e to the minus t naught here. And then you would get sine of t minus t naught times u of t minus t naught. So like what would happen if you hit the spring with a hammer at time t naught, it just sits there, does nothing right up until the hammer hits it, and then it starts oscillating after the hammer hits it. Here's one where I'm hitting the spring at time pi with an impulse of 3, and I again have initial condition of 1. So we have oh okay. So I was worried I'd made I made that minus error. I made a second ago here again, but no, that's the initial condition. So minus s plus 9x. So we solve for big X, and that gives us this, which this is going to give me a sine, and that's going to give me a cosine of 3t. So I have inverse Laplace transform of this and that. And this, again, is a sine, but since there's an exponential, we get sine of 3 times this shift t minus pi times u of t minus pi, and then over here, we just get cosine 3t. And then if you rewrite this as a case-wise defined function, you can go back and undo the unit step function formula and write it back in terms of cases. And what you got is cosine 3t before the hammer hits, and then you got cosine 3t minus sine 3t after the hammer hits. So these problems are not hard, right? So don't be scared of that problem in your homework about the hammer and stuff. Like it's not that bad, I don't think. Although I guess you could do, there are more scary versions of these questions. Like you could do something like, suppose you've got a spring which is oscillating back and forth, and you could ask the question like, if for a certain, you could ask like, what impulse and what time do you need to choose to make the hammer, to make the spring motionless after you hit it with the hammer? I think you could achieve that if you could impart the momentum. Like suppose like right before the spring is hit by the hammer, it's got momentum, say 10, right? If you could somehow take the hammer and hit it with a momentum of minus 10, then what would the momentum be after the hammer hits? The momentum would be 0. And so I think physically speaking, it's clear the spring should just sit, the spring mass system should just sit there, right? So if you could manage to do that, I think that's physically possible. And I think I've assigned a homework problem like that in the past. Did I do it to you guys this semester?
Yes.
I did? Okay, good. So that one may have more than one solution, because if you think about it, if you can do that in one cycle, you can do it in any cycle, right? If we're talking about a spring mass system without friction, the story repeats itself over and over and over again every cycle, right? So whatever you can do in one cycle, you can do in the next. So that problem ought to have infinitely many solutions. I'm probably just looking for one, though. So this one I think we might have worked last time, but let's look at it. And I don't think we did, but this is like the ones we worked last time. Suppose you've got y prime prime minus 2y prime plus y equal to the unit step function. We've got initial condition 0 and 1 for the velocity. We take the Laplace transform. We get s squared big Y minus 1 minus 2 times s times y plus y, which then gives us this. Then we divide. Notice that this is s minus 1 squared. So this is the partial fractions then. We do 1 over s minus 1, 1 over s minus 1 squared like that. And as such, that makes the inverse transform of this just 1 minus e to the t plus t e to the t. So then if I take the Laplace transform of f of s times e to the minus s, I get this evaluated at t minus 1 times the unit step function at t minus 1. And so in short, the answer to the problem, again, is obtained from a combination of like partial fractions and the theorems we worked out last time in terms of the unit step function. So yeah, there's the answer. And so like there's two pieces to the answer. There's the part which is determined by the initial condition, and then this is the part that is coming as a response to the the system having the force turned on at time 1. So there's one other thing I should tell you guys about. So I think we worked this example last class, but so I think that's a repeated example. So the other thing I should mention to you guys is the concept of convolution. So convolution is an important mathematical device because it gives us a way to take inverse transforms of things that might otherwise not be obvious. All right. And it also, well, there's a deeper connection with the convolution theorem and the theory of linear systems, something called the transfer function, which is important to engineering. Perhaps I'll talk some more about that Monday, but I just want to talk about this today. The convolution theorem is, what we want is we want the Laplace transform of the convolution to be the product of the Laplace transforms of the functions which are convoluted. So f star g is called the convolution of f and g. If you could define such a thing, f convoluted with g, to be this, then the inverse Laplace transform of the product of two functions of s would just be the convolution of their inverse transforms. That is something very nice. So let's work out, we can work out actually a formula for the convolution down here. So this says that there exists, basically the point of this theorem is to say that there exists something called f convoluted to g which satisfies this identity. And here's the proof of that. Well, actually, my bad. I think I've somehow skipped past the definition of convolution. Sorry, guys. Oh, here it is. Dumb. Stupid scrolling got me. So I should probably define the convolution before I state a theorem for it. So here is the convolution. You take f convoluted with g is defined to be the integral from 0 to t of f of t minus v times g of v dv. All right, this is the definition of convolution. So for example, if you calculate the convolution of t and t squared, you do the integral, it works out to 1/12 t to the 4th. Happy day. And convolution has lots of nice properties. It's commutative. It obeys nice linearity properties. It's also associative. Convolution with the zero function, 0. Yeah. But the main use of the convolution for us is this theorem here, the convolution theorem. And so if we calculate the convolution, the Laplace transform of the convolution, we have the integral from 0 to infinity of that. But by definition, the convolution of f and g is the integral from 0 to t of f of t minus v g of v dv. Right? And so since we're looking at the integral from 0 to infinity, this then becomes, well, let's see here. So this is only non-trivial up till time t. So if I do u of t minus v, then this is going to be only non-zero before time t. So this is a reasonable step, right? I'm just adding 0 to make this into an improper integral. So that's a legit step. Then I bring this e to the minus st inside the integral like so. And let's see here, what am I doing? I think I'm, whoa, what is that step? Okay, so it's okay to bring g of v out of this integral because this is the integral over t. So v is fixed here, I think. Oh, no, my bad. That might be a typo. That might supposed to be, I think this is supposed to still be a v. I think that's just a typo. I'm sorry, guys. Just that's supposed to be a v. And then I'm flipping the order of integration and I'm pulling the v out in light of that. But then you've got, this is the Laplace transform of the unit step function times f of t minus v. And so that, of course, is f of s times e to the minus sv, right? Yeah, that's that theorem we did last time. And then we have, oh, well, that's the Laplace transform of g, is what that is, after I pull the f of s out. So there it is, which is what we want. The Laplace transform of the convolution is the product of the Laplace transforms. Let's see what this does for us. See, this allows us to do, for example, this solution here. Suppose you're solving y prime prime plus y equals to g, where you have initial conditions 0 and 0, right? So we take the Laplace transform of the equation, we get s squared big Y plus big Y equals to big G. Solve for big Y, we've got y of s is equal to 1 over s squared plus 1 times the, the Laplace transform of the forcing function, yeah? We take the inverse transform of this. Well, we would be up a creek in general because we don't know, I mean, what is G? G is arbitrary. How do you take the inverse transform of an arbitrary function? Well, and how do you take the inverse transform of a, 1 over s squared plus 1 times an arbitrary function? Well, without the convolution, we would kind of be lost here, but with convolution, we just use the convolution theorem, see, because I'm taking the inverse Laplace transform of the product of this function of s and that function of s, which by the convolution theorem is just the convolution of the inverse transforms of this and that respective. But the inverse transform of this is, of course, sine t. The inverse transform of big G is little g by definition, and so that's the answer. The answer is, the solution is sine of t convoluted with g, all right? Which we can write down a specific integral for. Like this means the integral of a particular thing, right? Like I have to go back to the definition for a second. So like sine of t convoluted with g of t. Oh man, I didn't write it down. I was hoping I'd write it down. So let's write it down. So what would sine of t convoluted with g of t mean? It would be the integral from 0 to t of sine of t minus v times g of v dv. So this y of t would be a so-called integral solution for the differential equation we're just looking at. Right? I'm pretty sure if we were to do variation of parameters on this problem, it would bring us to the same formula. Although there might be a little bit of trigonometry between. Oh man, I went too far. So that's what sine of t convoluted with g of t means. Another example, if I had here y prime prime plus y equals to cosine of t. And again, I'll make the initial condition 0 to simplify our life. So if we just use the previous example, we've got now g equals to cosine. So the answer is the convolution of sine and cosine, which is this. All right? But you can do this integral. Adding angles formula for sine gives us this. So I have, let's see here. Notice the integral's over v, so the terms with t I can pull out. Like I pull out a sine t, this is cosine squared v. I pull out the cosine t, I've got a sine cosine over here. But we do these integrals, and we get this and that respective, which gives us 1/2 t sine t. Well, this is interesting, right? Because this is the tricky part of undetermined coefficients, yeah? You notice that this is cosine t is exactly the function that gives us trouble because it's overlapping the homogeneous solution, right? So we would need the method of annihilators in this case to pick up on the overlap between d squared plus 1, you know, having sine and cosine as fundamental solutions to this problem. And cosine of t, of course, is one of the homogeneous solutions, right? So, but notice that the convolution method automatically generates the t that we know that we need for this kind of solution. But anyway, there's much more to say here in terms of the theory, but I think I'll stop there for today. Yeah. Thanks, guys. Have a good weekend. Do, 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 do.